You got a clicker for the slides?
No, not yet.
Is she thinking about that, or?
I think she is, but
I mean,
otherwise I can.
Be your clicker.
I can click too. I'm pretty
you'll
easy.
have to walk back and forth. So I could sit here, worst case, and you could just point. You point, I click.
I might want to remind myself what I got.
I'm going to wait another minute because we still have people coming in.
And do you know this amplify for the online but not here?
That's just for the online, I think. Oh, no.
I guess it's here. Let's carry it. Hello?
Yeah. Try it again.
Testing.
You want more?
No, that's good.
There's more headroom if you need it. I haven't changed that podium electronics since it's about 10 years old now.
That one's on as well.
I'm going to go at 12:33. She's supposed to be bringing you a clicker, or?
I think she's looking into it, but no big deal if we don't have it.
I'll click for you. If that works, then you don't have to run back and forth.
I'll probably meander anyway.
That's all right. Okay. Thank you all for coming to this Epic Energy Seminar Series, October 18th version. We have today my friend and colleague Keith Evans. I've known Keith for a few years. He's the president of Kyma Technologies in Raleigh, right?
Right.
Kyma Technologies in Raleigh. Kyma is a company that makes gallium nitride materials and other types of wide bandgap semiconductor materials. He's going to tell us about that. Keith is also the president of the Power Electronics Industry Collaborative. He started his work at Air Force Research Lab on 3.5 semiconductor crystal growth. He's had executive positions at a number of companies over the years, IQE, Vigo, Crystal IS, before he came to Kyma in 2005. He is on the external advisory board of the NSF-funded Penn State-led 2D Crystal Consortium Material Innovation Platform, and a member of the American Association for the Advancement of Science. He has a PhD from Purdue in physical chemistry, so that's very relevant to the semiconductor growth regime. So he's sort of working at the realm where physics and chemistry and electrical engineering all meet in his career. So with no further talk, there's a sheet coming around. If you're a student especially, be sure and sign one of the sheets so you get credited for being here. And we're asking actually everyone to sign the sheet. So the talk is called Applications of Wide Bandgap Semiconductor Materials in Power Electronics. Okay.
Okay, you should be all set.
Just-in-time delivery. Thank you.
All right.
Thank you. Thank you, Ed. Very much. Thanks for inviting me to come up here or come over here, come down here from Raleigh.
Over and down.
Over and down. I actually took the first opportunity to ride my motorcycle more than about 20 miles. I came in last night It was harrowing on Route 85. We have a better route going back. But it's a pleasure to be here, and as you heard, I'm a physical chemist, so I really don't know a lot about electrical engineering and things. So you might wonder how the heck I ever became president of the Power Electronics Industry Collaborative. I'll tell you a little bit about that in a few. And I'd love it if it was highly interactive. You can stop me anywhere. The slides are a little bit kind of scrambled. Some of them I'm going to just skip, I think. But if anybody wants to just say, hey, can we go back to that slide, I'll be happy to.
So time frame is nominally until 1:30, so you can, yeah.
Now, where am I pointing? Up here?
Probably that way, yeah.
There. Okay, this is a rough outline. I was going to talk about material properties first. It's a little bit backwards, but because often you start with applications and market opportunities, but it felt kind of reasonable as it flows into what Kyma does and what the Power Electronics Industry Collaborative is all about. And I had mentioned in the abstract, we're going to talk about collaboration opportunities. Some of them are going to be implicit, but there's not much there that's explicit right now. Okay, over this way. Okay, on the materials properties side, so I think most of you have seen these tables, and there's a semi-infinite number of properties of any one material, so it's an interesting exercise just to decide which materials properties you want to capture. Let's see, this must be, yes. So the band gap, of course, is interesting, and the so-called wide band gap semiconductor materials is, I don't know if there's a formal definition out there, but it's nominally something with a band gap bigger than gallium arsenide, I believe. And so silicon carbide, gallium nitride, gallium oxide, aluminum nitride, and diamond fall in those categories. So do a whole lot of other materials. And of course, if you get a wide enough band gap, it doesn't look like a semiconductor anymore. It's more like a dielectric, I guess. So certainly carrier mobilities are interesting. Breakdown fields, especially for power electronics. Dielectric constants, always important for many applications. And we have this calculated thing here called the high voltage Balagha's figure of merit and the high frequency Balagha's figure of merit normalized to 1. And I could get you formulas for all that if you're interested, but that's their textbook as well. Professor J. Balagha, I think he coined the figure of merit term when he worked at General Electric in the old days, if you will, in the 50s and 60s. He's an eminent professor at North Carolina State, or UNC Raleigh, I think is what it used to be called. And then there's a whole bunch of other figures of merit, Key's figure of merit, Johnson's figure of merit, et cetera, that are very relevant to power electronics. And then thermal conductivity doesn't enter into these figures of merit, but certainly it's important for applications. If you're going to push a lot of current density through something, you're going to dissipate a lot of energy. So that's not tracked with most figures of merit, but I've got it down here. And then as Professor Balagha himself told me, these numbers don't mean anything, or they mean way less if they're not measured on the same piece of material. So you can find yourself a lightly doped piece of gallium arsenide with a real high electron mobility, but it presumably has a reasonable thermal conductivity, but it might have trouble in one of the other categories, and it doesn't have any holes, so how are you going to get a hole mobility? So you really got to make these measurements on the same piece of material. Here, this is kind of this is a much higher number that's typically used for gallium nitride. You see 100, 120, 110, 130, and that's because those measurements are on highly defective gallium nitride. But at the end of the day, you see these big figures of merit kind of go up as you go to the right. So these materials are increasingly of interest for power electronics because that's what that figure of merit's all about. And here is a plot of the on resistance versus breakdown voltage on a log-log plot that the high voltage Balagha's figure of merit speaks right to. And so you can see very clearly that silicon carbide's way better than silicon for a given blocking voltage to get a low on resistance. GaN's quite a bit bigger, and it's a log scale, right? So GaN's quite a bit better. Gallium oxide looks tantalizing, but the previous slide shows it's got low thermal conductivity. One has to think about that. And then the C there is for diamond, and then even aluminum nitride's even further out. So these things are hugely of interest to many folk. And just we had an exercise with Sandia National Labs who formed what they're calling the ultra-wide bandgap semiconductor guild, where they define ultra-wide bandgap as something with a bandgap above gallium nitride. So an arbitrary definition, and they're spending a lot of time on aluminum gallium nitride. Yes? Sure. Do this. The table? Yeah. Yeah, I think all these numbers are somewhat arguable, especially the less mature materials. But I mean, I used to hear 6.02. You know, it's around 195 nanometers optical band gap. Zinc oxide should be on here. Yeah, it was a little bit of an oversight. It's got even a lower thermal conductivity than gallium oxide, I believe. But yeah, it's certainly a material of interest. There's others. So good questions. If you look at this thing here, this is a term, I used to hear these various terms, and once again, I was more of a gas surface scattering physical chemist by training, and then I got into the solid state world. Well, we hired a young man out of Case Western Reserve University about a year ago, and he got his PhD growing heterovalent ternary nitrides, where you replace half the group 3s with a group 2 and the other half with a group 4. And all the electrons all add up and everything, and if you choose adjacent to gallium, you end up getting something with a lattice constant very close to gallium nitride, and you get, one would hope you get carrier mobility similar, but there's such an array of crystalline sublattices that these metals can occupy that it destroys the phonons, and that's the thinking, and they've got good theory work going with that. So, but these should be, you know, you can do the aluminum nitride analog, just look in the periodic table what's on the other side of the aluminum, and so that's another one that could go into the table. So this one I just tweaked up this morning. In fact, I used to have no diamond and no gallium oxide on here, and it shows kind of things getting bigger and bigger and older technology, if you will, and all these top guys here are grown from liquids. And of course, if you got a big pot of liquid and it's super saturated, you put a seed in it and you have a temperature gradient, you know, you would think you might be able to grow some big crystals. And that, indeed, I mean, history has taught us that. I mean, I've seen, you know, you know, sapphire boules like this big. They're really impressive. And of course, silicon is highly perfect how it's being made. But diamonds down here, it's real tough. This is so-called high pressure, high temperature diamond, grown mostly in China after General Electric, your old employer, gotten some patent battles and licensed the IP for these techniques. And then gallium oxide's sort of new. I think it's about similar in difficulty to aluminum oxide, but it only came up, I think just nobody really jumped in hard until maybe 5 years ago. And it's got a lattice constant that's close to InGaN, where the indium content would be appropriate for trying to solve the green gap problem in solid state lighting. So I think it initially got developed as a substrate for InGaN growth, but now it's turning into its own beast because of the high Balag's figure of merit for it. And this one I just kind of inserted, and it's not meant to be complete, just to show you the array of companies in the U.S. that are in these bulk materials. Nitride Solutions making aluminum nitride by a couple techniques. Hexatech has made some really beautiful boules of aluminum nitride. Crystal IS had world record, I know, when I was there, and recently I guess they've come out maybe surpassing the other two with a 2-inch diameter aluminum nitride substrate. Hexatech is active. They're in Morrisville, and you know, I think they're focusing down on a materials plan and stepping away from a device plan. Because if you have this really great material and you're the best, you can capture more value if you make devices out of it, but you need more money to make the devices out of it, and so you have this game with venture capitalists, and I think the early investors in Hexatech really wanted to see UV devices and power electronic devices come out, but I think they're settling down into enabling their partners to do that. Still,
For the students, at least 3 of those companies are in North Carolina, but maybe more, but
Hexatech, Kyma,
and Cree.
and Cree, of course. Yep, yep. And CO Diamond's not too far. It's in South Carolina. I don't know them real well. And this one might be in South Carolina now, moving up from Florida. This is up in Chicago area, Midland, Michigan area, Amont. Of course, you know Amont. That's up in New York. 6 Point Materials out in California, and Sora, yeah, in Goleta, California. Okay. So this, I dusted off a couple of old slides because Ed and I were just talking about how we feel like we're in this rapidly evolving technology space, but sometimes things feel like they don't move as quickly as we would like. So this is an old slide just reminding us why you want a gallium nitride substrate under a gallium nitride device, for instance. So here, there's tons of gallium nitride on silicon carbide made at Cree, for instance. Certainly all their early day LEDs were made that way, and they've made a ton of RF devices, GaN on silicon carbide, but it's highly defective material. Not that that's Cree's, that's just a typical one in the literature. And if you go GaN on a GaN substrate, at least in that field of view, you won't see any extended defects. And the top can look really beautiful, and the top cannot look real beautiful for the heteroepitaxy case. And so this kind of logic carries through for all semiconductor materials. I challenge you to tell me one device out there in volume that's not grown on the native substrate. And there are some, like almost all the blue and green and white LEDs in the world. But aside from those, all the gallium arsenide, indium phosphide, silicon carbide power devices are all homoepitaxial. So we're always pushing to get the substrates developed if Mother Nature allows us to. And so, unfortunately, it's difficult to grow GaN. That one slide I showed, that a lot of the wide band gaps, you can't grow them from melt. Although there are liquid phase techniques being used, and I'll go through some of those. But when I joined Kyma in 2005, we were singularly focused on trying to make GaN boules and slice them up into substrates like this. And we've demonstrated maybe 3 or 4 sliced from one boule, but not high enough quality and low enough cost to make a difference. Almost all the GaN substrates you can get today on the market are grown this way. Like for instance, Sumitomo Electric, at least according to what's in the open literature, they start with a 111 gallium arsenide substrate that's pretty cheap, so because you're throwing it away after each growth, to my understanding, and then they grow less than a millimeter of GaN, and they yield 1 substrate from that. And there's similarly, I think Hitachi Cable was starting with sapphire, and Kyma would start with sapphire, and we do this today. But it leads to a wafer that has, and I don't have detailed characterization results here, but it has lattice lensing, it's called, where if you did XRD across the wafer, you'd see the position is varying because the offcut of the surface is varying as you go across the wafer. It has to do with nuances of how this crystal growth starts when you initiate it, and it's an issue. So GaN substrates on the market have gotten cheaper and cheaper and more readily available, but I think the device people kind of hit a wall. They're not getting great yields, and so still people are primarily using foreign substrates for their devices. Well, the substrate people, including Kyma, continue to try to innovate to create something that's going to get real volume traction. And I think we're on to something now. I have some slides to show you that. But then kind of an intermediate between just using, instead of making a GaN on silicon carbide FET, for instance, one might consider, what if you put a thick buffer layer on there and then put your FET layer on top? Would that be of interest? And certainly you can knock the defect density down an order of magnitude or 2 relative to straight heteroepitaxy. So this is an example of that from George Brandis provided this from Cree years ago, and just showed how different buffer layers and then freestanding GaN all showed different extended defect levels as measured by AFM, and as it should be. But certainly the device guys would rather have 2 times 10 to the 7th and 4 times 10 to the 8th to grow their epi on if they had a choice. So we're all working towards that. This is a, I won't take you all through the slide, but I'm going to go back here. If you were growing your epi on here, your device epi, you wouldn't be so tempted to grow your own buffer layer because you got a really good starting place. But over here, you might need to grow a buffer for a while. So this next slide just shows that the time taken to grow these different layers goes down. Let's see, do I have a cycle time here? So the defect density is getting better and better as you go from left to right, and then you could add up these times and the cycle time goes down. And it turns out that, for instance, for LED manufacturing facilities, half of their capital equipment is spent on the MOCVD tools, and those MOCVD tools, about half of their growth cycle for making an LED is spent on buffer layers. That's really expensive stuff. So, Kyma and others feel like we can give you the buffer layer cheap and an even higher quality. This one is again showing how you can reduce the cycle time by growing on a GaN substrate on the top. So I think this is maybe the last of these old slides pulled from the 2009 solid state lighting manufacturing workshop. Ed, I'm not sure if you were there. I forget if this was maybe Los Angeles, but I got up and made a prediction that the market was going to move on from, back in the early days, statements made by large companies to the U.S. Department of Energy solid state lighting group was that we don't need any work on substrates. We have what we need. And you can see that that's not the case today. They're still arguing over what exactly they want, but everything's being tried, from freestanding GaN, that's SORA, right? GaN on GaN LEDs, to there's lots of this, a lot of aluminum nitride PVD tools in the market to put a thin nano columnar structure on sapphire and pattern sapphire to help the LEDs. This is a little bit adjacent to what's important for power electronics. Commercial, these are definitely commercial, and there's some of this out there too, because some of the really big fabs have these fully depreciated MOCVDs sitting there doing nothing. Well, they fire them up and they put GaN buffer layers on them and then pull them off and use them to manufacture. Freestanding is a term used for a substrate that's all gallium nitride. Native implies to some, so it might be misused here, that it was grown by a bulk growth technique from a gallium nitride seed. But these terms get really mixed up out there, and maybe I'm part of mixing that up. I used to try to really get it straight. But Leo Showalter from Crystal IS used to argue with me, you guys don't make native GaN. I says, it's 50% gallium, 50% nitrogen. It seems native to me. And then this here was something that we thought, and this parallels the people doing smart cut technologies, why have this 1/3 of a millimeter of really expensive material when really it's only the outer monolayers that you need to do good epi. And it turns out the high performance devices out there, a whole lot of the substrate is removed in power electronics, RF electronics, and LEDs. So it's really just to enable high quality epitaxy is that surface layer. So there's groups working on, and Sumitomo Electric was partnered with Soitec to take their freestanding GaN and lift off maybe 100 nanometers and set it on something else. And that something else is cheap, and it might be a good thermal conductor. But we've got something going on today I'll tell you about in a moment where it's a good thermal expansion match to GaN. So you can't just put that GaN on anything and then have it survive the MOCVD or MBE growth cycles. The whole thing can potato chip and crack and everything else. So I kind of missed it back in 2009 that we wanted to worry about thermal expansion coefficient up there. But live and learn, right? So here's a beginning of a few slides on how GaN has grown. And this is not too dated, but I recognize these are Mitsubishi Chemical Corporation's HVPE grown GaN that they've shown these many, many times. This is, you've probably seen these in some articles. This is a mono's gallium nitride grown by a monothermal technique. A mono, it was funded by Nichia and exists in the northern part of Warsaw, Poland. And they've had interesting, we've been partnered up with them. I'll tell you more about that in a moment. And then there's sodium flux technology that I used to just discount. That'll never work. And then high pressure nitrogen solution growth at the Polish Academy of Sciences has made, I think, arguably the best material in the world, but kind of in thumbnail form factors. So 4 different well-known techniques to the GAN people out there. So I'll tell you a little bit more.
Can I
Of course.
interject that when he says high pressure here, some of the people in this room know that we're growing material at high pressure, but this 40,000 atmospheres.
At least.
Ours is like 2 atmospheres,
Yeah.
so it's a totally different thing. We're growing epitaxy, and this is for single crystals. Sorry, thanks.
That's okay, sure. Okay, well, it's not doing it anymore. Let me do this.
I was always told that what they're doing in Poland might not be doable in the United States.
Having trouble
Did it get
advancing.
hung up?
Yeah. So there. Maybe just click that. Okay, we'll get there one way or another. So this, I had mentioned, I had kind of discounted this. Oh, this is the high pressure growth. Okay, that's not a great slide for that. You can just do current from current. That's what I did. And I think it's, no. I can just do it from that window too if you want. Yeah, maximize that. Well, I'll talk a little bit while Ed plays with those a bit. So the sodium flux technique has really come to fruition, it appears, and a lot of people discounted it as never being a real player. And then our chief science officer went to a conference in Germany about 2 years ago, and he saw a 6-inch wafer shown. It's a relatively beautiful wafer, and so the wars are on, and it is a real player. Meanwhile, Kyma partnered with the Mono of Poland on an ARPA-E switches program, and we thought that we were the smartest group in the world doing this, or the 2 groups coming together, but it turns out others are pursuing the same thing, and that's where we take in a monothermal seed grown with maybe 10 to the 3rd defects per square centimeter, and then rapidly grow on it by HVPE and make boules. So the monothermal technique is a wonderful growth technique from a structural quality perspective. But yeah, so that's a high pressure nitrogen solution growth. Actually, I think these are mixed up. This is sodium flux, and that's my fault with the slides. I'll fix that if anybody's going to run away with these slides. But yeah, go ahead and step down. It's just showing incremental progress, but it is pretty sure it's sodium flux technique, not high pressure. I didn't change the title. So this is the monothermal technique in Poland, and it's made beautiful stuff. Okay, go to the next one, Ed. And now this is the real sodium flux. So really small stuff, but kind of pretty has been made. And then what I'm telling you is this is up to 8-inch diameter to my understanding now. So this is that's less than a centimeter form factor there, but it's really advanced over the years. So where are you at? Why don't you go to 22? Or no, where are you? Yeah, go to 22, that one. And then there's HVPE. So you saw this on a different slide, but these are Mitsubishi Chemical grown. And Kyma's grown some that look close to this beautiful, but most of the time they have a surface morphology. And you can grow really good crystals and then lose the quality of the growth fronts, and then you grow junk on it. But if you mill that away, you got good stuff underneath. This is one of the few I've seen where it stayed good and didn't need to be machined off. Why don't you go to the next one? So this slide here, I just found this on the web today, and I found there's minimal web footprints for this, but I learned at a meeting on 6-inch gallium nitride power electronics at UC Davis about a year and a half ago that there was a new consortium in Japan, and by the time you hear about it, it's already an older consortium. But I had a close colleague tell me that $200 million put into it. We had a gentleman from Toyota Corporation tell us about it at UC Davis, and they're mentioned here, Toyota Technological Institute, related to Toyota. And they're going after 8-inch and then 12-inch diameter freestanding GaN, or bulk GaN, if you will, or native GaN. And somebody asked him, well, what growth technique are you focusing on? And he said, many. And then the head of this consortium included Professor Amano, Nobel Prize winner, so knows nitrides in general really well, but also had Professor Mori from Nagoya University, and that's a sodium flux technique. So it's kind of like opposite world, where we all thought sodium flux was the loser. It's kind of leapfrogging to maybe being the winner. And we know it's being incubated at least one significant U.S. company as well. And we'd love to take it on ourselves. So Ed, you want to step? So, okay, let's move into applications a bit. We've already kind of talked around applications, but here is a picture of the whiteboard, or it was, of a slide presented at Mantech conference about 3 or 4 years ago by Toyota. And it's, if you zoomed in on it, you'd see the all-nitride car or an all-nitride vehicle. And we actually had Toyota in our facility back when they first came out with the Prius. And they said, yeah, it's a wonderful car, but we have to do better. They have, and I've seen it at Oak Ridge National Labs, like a bank of silicon IGBTs this big under the Prius for, sending juice back and forth between the battery and the motor, and from the regenerative brakes, and then from the gasoline engine as well, because it's a hybrid. And those electronics are about 90% efficient, so 10% of the electricity running back and forth is dissipated as heat. Well, silicon doesn't work when it gets very hot, so they got to do water cooling on it. They didn't have any excess water cooling capacity on the car, so they put another compressor in there, and big pain in the butt, cost and reliability issues. And so they were looking forward to getting rid of all the silicon, or at least the silicon that was really getting them in the manner I mentioned, and going to either all nitrides or all silicon carbide. And of course, more recently, gallium nitride showing up in the headlights on the cars. You can get gallium arsenide on the brake lights. So the automotive industry is looking real seriously at the wide band gaps for power electronics. This is just a picture of I forget what it is, from International Rectifier. It had on their website how if they go from silicon to GaN on silicon. Not bulk GaN, just GaN on silicon, they could shrink things like that. So huge lighting market and a real strong push from power for these materials. Go ahead, Ed. And this slide here is, there may be a newer one available. Usually the nuclear people in the U.S. And the nuclear side of Department of Energy publish things like this. Where's all the electricity coming from and where's it all going? Tons and tons and tons of electricity being used, and energy in general. And we are all hugely motivated to be more efficient users of an increasingly better mix of these, right? Coal, we want to go away. The fossil fuels, we'd like to just leave them where they are and not pollute the air. So this is a big driver behind everything. Go ahead, Ed. And so that plays into the lighting and power electronics side, but there's also monstrous applications for RF electronics, and laser diodes have been this kind of thing that really got GaN substrates going for the Blu-ray disc. Remember when the Sony PlayStation 3 took 1 or 2 years extra to come out, and it was because they didn't have a good GaN laser for it yet. They finally got there, but then it's been sitting and kind of trading sideways, if you will, or even going down in popularity because there's other storage methods that are becoming more important than optical storage. But still, but more recently, there's projectors, there's pico projectors on phones, even, you know, laser-based projectors for movie theaters are in development. So I'm thinking this is going to take off yet. And then if you look at the properties of LEDs and laser diodes, they're approaching each other, at least from, you know, from certain players in terms of current density. And indeed, laser diodes are being used for lighting and for headlights, but not shooting the laser beam, but, you know, defocusing it, but using the high energy efficiency the laser diode can have when it's at high injection levels. And the communication side, I only learned this in Orlando 2 weeks ago at the International Workshop on Nitride Semiconductors. I'm a little late to the game, I guess, but 5G communications is being pushed out to really high frequencies. And I still haven't shown you the Kyma slides, but I had a guy tell me, just quit chasing power, don't worry about LEDs, go after 5G because that's going to go like this. In fact, he said that the Japanese have been real clear that they want all their new electronics and cell phone towers in place by the 2020 Olympics. So that's their milestone. And so a lot of groups are reacting to that. Some more proactively. We're just reacting now. Go ahead, Ed. Let's see what we got. Yeah. Yes.
So is the lighting so far the biggest market you mentioned?
Lighting is the biggest one with the wide band gaps in it. I think power could be as big or even bigger, but there's a question of how much silicon will be replaced. And there's people that, I mean, we're in some conversations, they say if you can just get this to, you know, you get your GaN on this novel substrate to 10 to the 7th level, it'll just wipe out a bunch of silicon out there. So there are revolutions that are pending in the power electronics space. But this Li-Fi here, this thing is supposed to have like a $67 billion market at the device level. Now that's emitters and detectors, and so I don't know what that looks like yet. I mean, if it's free space communications, it should be somewhat wavelength agnostic. You just got to put a wiggle on, or if it's the LEDs that are lighting this place, if we have any. If you put a high-speed wiggle on that, you can put, you know, high-speed communications and that your eye doesn't see. So that's a really intriguing market. And then you got 5G over here. You got all these things. I mean, we're hearing about airplanes that have, you know, a high-end inverter and power electronics all down in the wheel itself. So it's not going to be driven by some other motor. The world's changing, and the wide band gaps can play into all these spaces. Go ahead, Ed. So a few words about Kyma specifically. You can go one more. So these are recent pictures. Maybe you can tell with me, but this is Heather Splon, our Chief Operating Officer. She's a Duke PhD, EE, and she does all of our legal work and monitors daily operations and finance. The brains of the operation on the science side is Jacob Leach, PhD from Virginia Commonwealth University under Hattis Moorcock's direction, and his dissertation was on indium aluminum nitride, gallium nitride, FETs, lattice matched to GaN. In fact, he did that work as a subcontractor to Kyma. We had Missile Defense Agency funding for that effort. Okay. And here's the same plot I showed you earlier, but now I color-coded it. Kyma is actively developing all these materials. I didn't list them all on another slide, but we have activities in all these. Go ahead, Ed. So here we are. There's Cree, there's Hextech, there's your Raleigh, or your North Carolina wide bandgap companies. Your old buddy from GE's in the area too, and I think he's using wide bandgaps as well. What's Stephen Valence Cell making sensors. And then, of course, this is the Triangle region, and I don't know if anybody has a favorite basketball team there. Maybe it's the Charlotte team that's not shown. We have 2 facilities, very modest facilities in a modest area, but combined 13,000 square foot of high tech space. Go ahead. And these are pictures of reactors that we've built ourselves over years, crystal growth tools, we call them more commonly. Initially, the company was started by North Carolina State professor Jerry Cuomo and his grad student. They were making PVD materials. It's DC magnetron sputtered plasma vapor deposition. They were trying to make bulk aluminum nitride and gallium nitride in the early days, and then Drew Hanser joined the company and pointed them towards hydride vapor phase epitaxy for GaN, because that was getting some pretty good airtime by other groups, including ATMI. Cree invested in Kyma, but at some point around the 03 time frame, they wrote off their investment and they acquired ATMI's HVPE group. So then later they sold all those assets to Mitsubishi Chemical Corporation, or as many as they could. It's a really dynamic field. But we've built bigger and bigger reactors over time for more capacity, for shipping larger quantities of materials. We built this one on steroids as an 18-inch diameter platter holding like 37 2-inch wafers, or multiple 6-inch wafers. And we actually built this. It's got a different color for GT Advanced Technologies, and who had licensed this technology from us, but they went bankrupt after doing a deal with Apple that didn't work out well for them, and we've negotiated our rights back, so we have the IP for this again. Took kind of a left turn at some point making two-dimensional materials, and Ed mentioned I'm on the Penn State advisory board for their two-dimensional center. So we've been growing moly disulfide, tungsten disulfide, have huge interest in graphene and other materials. It's a different world because you're trying to make one monolayer, and when we started our roots trying to make bulk, it's just completely different way that you have to think about the crystal growth. Really makes MBE look enticing. And then more recently, we are involved in diamond growth, and this is a plasma-assisted vapor CVD system at Michigan State University. It's our partner on an Army-funded diamond effort. Go ahead. And this is, I just got two shots of some diamond results. It was an interesting proposal topic that came out that said, hey, the world of diamond is really exciting for electronic applications, but as I showed on one plot, you can only get about 7mm sized bulk diamond films by just growing it by high pressure and temperature. And they said, so there's maybe 3 ways that one could get large area electronic grade diamond. One is to slice layers from that bulk 7mm sample and stitch them together. So here we took a 7mm by 7mm approximately wafer and intentionally cut it and cleaned up the edges a bit and put them next to each other and grew over it. And so here's after we grew over it to see if we could prove that you could make these things stick together. Now it's proven by others, perhaps I think a group in Japan and maybe in Singapore as well, that one can do that, but the U.S. is trying to get a U.S. group to do it. So we successfully got these things. Go ahead, next slide, to grow over. In fact, it looked pretty good for the first shot. So here it is at 100x magnification. There's a boundary region there. But we have reason to believe that this surface morphology is pretty good. We're told by the experts at Michigan State. This could, in principle, support a high-performance electronic device. Probably not going to be great yields at where these things join, but if you could somehow make a really big wafer, and so what you got some stitched regions or interface regions that are yield losses, that would be a major step forward, though. So that was one approach. Another approach is to take the really tiny high-quality material and then grow CVD. You can make it thicker and then flip it over and make it thicker and flip it over and make it thicker. That seems like worse than watching paint dry. And then the third approach is to take polycrystalline material, which you can get in pretty large area. For instance, 2-6 Corporation supplies that. And we've seen that material because we're actually growing some GaN on that diamond. If you could enhance its properties to where it was of electronic grade. So I think the Army's funded all 3. We're the ones that are doing the stitching. And we're all at phase 1 levels, and we'll see who moves on to phase 2. But we like our progress so far. Go ahead. So this is one of, I think, 3 focus slides on, I showed you the gallium nitride substrate prediction that I put out there in 2009. where you'd end up with this smart cut of gallium nitride on something that was cheap and behaved well otherwise. So we had in May of 2015, not too long ago, we had a group come to us and say, hey, we've got this highly engineered substrate, and we'd like you, and it's got GaN on the top, but we'd like you to make that thicker by HVPE and see what you think. And in retrospect, well, it's turned out really well. So we're adopting this deck of slides. So these are extremely true statements that GaN on silicon, it's out there in volume now, but it's barely getting to 600 volts. Going to 900 is difficult. The yields are tough at 600. Going up an area, the bow scales as the radius of the or the diameter of the wafer squared. So to get the cost down, they want to go to 8 inches and then to 12 inches and leverage silicon fabs out there with equipment in that space, but the yields are horrendous. So they're really done a marvelous job of getting any product into the market at all. But to move forward, they've got some serious epi and issues that are tied to the substrates. GaN on silicon carbide, a fellow that approached me, and I sort of would love to say who it was, but I won't, at the International Workshop on Nitride Semiconductors in Orlando 2 weeks ago, said the 5G is not happening for the GaN on silicon carbide people because they just can't get their costs down. The silicon carbide's too expensive. Furthermore, I don't think it's available in volume. Well, I know it's not available in volume at 8 inches. It's been demonstrated at 8 inches. I don't even know if you would call it true volume at 6 inches. And to get your costs down, you really got to go to larger diameter because you make so many more devices per unit processing time, perhaps obviously, once you get past the epi. GaN on sapphire, they're pushing the larger diameter. But what happens, they have a bow problem. So they want to get their costs down, so they go to large diameter, but the bow is so bad that they make the substrate like 3 times as thick, which hits them on the cost side again. So and then vertical power devices, you know, most of the world of high power silicon electronics are vertical devices, I'm told. And, you know, you have so much larger area when you flow current vertically than going along the skin of a FET. You can have much higher power densities. So it needs a good vertical GaN substrate, and they're just not available yet. They're coming along. So the market really needs something better. Let's go ahead. So we talked to RPE about this. I'm going to go even further back in time where we said, look, these guys, they're making the perfect GaN substrate, and it can be cheap, but it's only available a couple inches in diameter. The world needs 6 inch and then 8 inch. So instead of them, well, let's have them focus on just making bigger and bigger and bigger. You probably can't see that, but this is a 2 inch curve, 4 inch, 6 inch, and then there's an 8 inch that's off scale. So let's partner with Amono, the company in Poland, and have them work on just making that bigger and bigger, and then we can take that and rapidly grow on it with our HVPE process and quickly get to where we don't need these anymore at 2 inches, so they can work on 4 inches. Then we won't need the 4 inch long after we get our boules because we can make our own seeds, etc. Looks great on paper, and we had the world record holder in vertical GaN devices on the team, and then we couldn't get any more material from Amono because they went bankrupt. So go ahead. And in fact, yeah, that's in the news. It's kind of hard to find, but this is an article that I think translated from the Polish. So go ahead, Ed, and one more. So then we did what we call a pivot, and we said, well, let's try to find another monothermal partner. We got Sora on our team, and we also 6 Point Materials also. I thought their symbol would have been here, but so it's the same other stuff. We're just trying to diversify our monothermal seed supplier. That didn't work. And so next slide. Now I'll skip that one. Next slide. That's just reminding us of this funny thing up here. So we've partnered with this group that came to us in May of 2015. They have a highly engineered material. They have special coatings on it. And then they put a smart cut thin layer of silicon on there using Navy technology. And these materials are picked to match the thermal expansion coefficient of gallium nitride. And they asked us, could you grow some GaN on there? And we grew maybe 30 microns pretty quickly. and had narrower X-ray line widths than we'd ever had on the thousands and thousands of GaN on sapphire wafers we grew. I mean, it's not quite as good as GaN on GaN, but it's much better than the GaN on sapphire. And we were really surprised because it's got silicon in there. I mean, we've always treated silicon as like the enemy, but that's if it's a bulk silicon layer, it is. But this is a thin silicon layer. So this stuff's looking pretty hot to us. And so we gave it a name, and we're marketing these we're calling them evaluation materials. Yes.
So what is it about the silicon that allows you to get that tensile quality? Is there anything unusual about the crystalline in that configuration?
You know, not that we understand all this. We think this is thin. I mean, certainly it's crystalline silicon, so there's a crystal surface to nucleate growth on, but we believe that it's compliant and moves as this expands as you heat it up and contracts with it as well, so that this stuff doesn't crack when we grow it on there. Now we can crack it, we have, so it's not completely strain free, but so that's not a great answer, I feel like. So it gives, you know, we don't think the defect density is any lower than if you grew on a bulk silicon wafer. We've just rendered ourselves way less vulnerable to cracking and surface morphology. But once you get away from cracking, so Kyma offers a GaN on silicon product. We'll give you up to 0.5 micron of GaN. Anything after that, it cracks. Now you can put an innovative buffer layer in there like many groups have, and I think all the groups that have a GaN on silicon power device out there have developed one, licensed one, what have you. And that's usually aluminum nitride, gallium nitride, AlGaN, superlattices, graded layers, and all that, just to mitigate some of the strain effects so the top part doesn't crack, but never do they get these thicknesses. So we have the freedom to add another 10, and we're working on 100 microns. In fact, we're working on growing bulk on there. And if we can do that crack-free, the defect density drops with thickness. I don't have that slide, but we're able to. So I think we're already an order of magnitude lower than any GaN on silicon power device out there by just doing this, if not 2 orders of magnitude. Okay, Ed. And we have established a partnership model with our partner, who's a Silicon Valley company, a U.S. company, in which we are going to provide tools to the market for growing those films, and they're going to supply the materials, both using fabless strategies. So our tools are being made by I think it's up here, a world-class OEM tool supplier. So it turns out, you know, Sears doesn't make refrigerators, they sell them. To my understanding, Veeco doesn't make MOCVD tools, they sell them. Others make them for them. So and if you look at the core competencies for making tools in volume versus doing research on next generation materials, they're way different. So we hope we're reasonably good at the latter, but we know we're not the former. We've learned that the hard way a couple times. So we have a fabless strategy here, and those materials are going to be made in volume through a fabless strategy by our partner. If you go to the next slide, it kind of lays out this model in which, and Quora is going to be speaking at Power America in November at the PEIC member meeting, and hopefully they're going to show something quite similar here, where their foundry will make their materials, and they will market the materials. Our OEM tool maker will make the tools, and will market the tools, and their foundry, we're hoping, will be the best and first customer for the tools, because obviously they need the tools if they're going to do the HVPE overgrowth, which we've been doing. And then we're jointly partnered on seeking U.S. R&D funding, and we've been successful at pivoting 2 Kyma projects to a partnership with Quora. And there's some PR out there to that effect, so hopefully we'll hear more at the PEIC meeting, which I'll tell you about in a moment. Go ahead, Ed. So introduction to PEIC, next slide. So PEIC is a nonprofit group. It's membership based, so most members pay a membership fee, and we use those fees to do things according to our mission. And you know, we have monthly board meetings approximately. We have 4 quarterly meetings, and one of them is an in-person meeting. That one's coming up You'll hear a little bit more about that in a moment. Next slide. So the vision is of the world of the U.S. as a global center of worldwide power electronics. You know, I don't know if anybody here has ever seen a television that was made in the U.S. When I was a kid, they were all made in the U.S. It was RCA and Zenith, and the PEIC was founded by a gentleman from Infineon, from General Motors, from Delphi, might have been a couple of others in the mix, and the question arose, you know, Infineon, a German company, but with U.S. sales offices and development offices, was trying to get their IGBTs, which were state-of-the-art, into next generation GM cars. And GM said, love to have them, but we're not buying IGBTs. We're just going to buy the whole drivetrain from one company. And we've already settled on who that's going to be, and that's going to be, I think it was Hitachi Cable, a large Japanese firm. So Infineon said, well, we know Hitachi Cable, so we'll go wine them and dine them and see if we can get designed in. Well, it wasn't happening. It's not how it happens in certain countries, and a lot of that's changing, but there was no way they were going to, so it was going to be like TVs is where it was going to go unless we do something about that. So we're trying our darndest. So lots of goals. You can see all that there. Let's go to the next slide. Some of this shows out. Where the PEIC is interested in all power electronics, even little doohickeys that go in cell phones and computers, but also the big stuff up on the grid and elsewhere, trains. Go ahead, Ed. We're focused just because the world of power electronics is so huge that you can't focus on it all. So we somewhat arbitrarily, but I think it was the founders that drove these three sectors. And I have to remind myself what energy efficiency means, because you want it in everything, but we've taken this definition to be grid and lighting, etc. Excuse me. Let's go to the next slide. So here's the board of directors. I got Dean Henderson from Infineon. He's yours truly. We've got Jem Bascari from Quora Technology, I was just talking about. And he's bringing a really important view to the PEIC, because he was formerly many years at Micron Technology, so a true international player, and understands, it's scary what he understands and the implications on who's going to win in some of these battles, because it's no longer good enough to just have a super high performance, high yield, excellent manufacturing facility for making one device, because your costs will be lower if you can have that 10 times as big and make 10 devices. And so there's a critical mass, and he's got the critical mass of understanding, I think, as to what one needs to do to be successful, and it's influenced our fabless strategies. So we're not going to try to push boulders uphill as much as maybe we used to. John Wren with Argonne National Labs, Julian Stiles with GaN Systems, speaking of GaN on silicon, and AJ Lastly from Delphi. So you might wonder, because you got to be able to tell already I'm not a power electronics expert, how the hell did I end up being president of this thing? And what happened was we wrote a nice proposal. I can't take too much credit for that. I had just joined, Kyma had just joined the PEIC about 2.5 years ago, and we were selected for NIST Amtech project, had $500,000 to study the supply chain, and I was the only one with real government contract experience, so they kind of volunteered me to be the new president of the board. And it's been a joy, and I hopefully learned a bit and helped the organization a bit. And I know there's been some good, but yeah, I'm not a power electronics industry expert. Actually, I don't know that anybody up there is. They all have, maybe Dean's the closest, and Jem's a generalist, darn physical chemist, double E. So we're a mixture. Next slide, and you can see the membership has grown nicely. We're up over 23. I lost count recently, and includes a couple stealthy players that don't want to be mentioned until the right time, and I'm hoping they come out in November 2nd and 3rd at Power Electronics, or at the Power America facility at NC State, where we're going to have our 4th in-person member meeting, and those are open, so you all are welcome to come. Last year we had the meeting at the Hewlett-Packard headquarters. It was put on by Keysight Technologies. It's kind of the old part of Hewlett-Packard or Agilent. There was so many recarving of that company at times, but that was a pretty impressive facility. Before that, at HRL in Malibu, California, who sponsored the in-person meeting, and then before that at Infineon's Livonia facility. So growing the organization pretty well. Go ahead. And here is a partial mix of current members. It's most of them, I know that. This SUNY Polytechnic is really, there may be another symbol added to that, but that's the New York PEMC, Power Electronics Manufacturing Consortium. In fact, they were competing head-to-head with what became Power America, and there are many groups trying to win that contract, if you will. Power America got the DOE support, but New York PEMC said, well, we're going to do our own thing. So they've got an 8-inch silicon carbide line going. It's spread out a little bit. This is SUNY. The old SUNY Albany is now SUNY Polytechnic Institute. Okay. Yeah, your old stomping grounds. But they've got packaging going in Utica, I believe, as well. And International Rectifiers needs to come off because they got absorbed by Infineon. And we've been trying to get Cree forever to join. And because Infineon might be acquiring Wolfspeed, we're going to get them the other way. So next slide, please. So there are benefits to joining. It's a huge networking opportunity. We're revamping the website so there can be members-only collaboration going on. So it's something I would, if you're interested, just get a hold of me and we'll make that happen. Let's see, he's clicking. Nope, not that. You're gonna have to do it. Yeah. Getting close to the end, everybody. I don't know how we're doing on time.
Where do you want to go?
The next slide.
This is the weirdest PowerPoint mode of operations that I've ever seen. Yeah. We're making it good.
So this is a little more about that member meeting, and I'll show you the agenda. It's still draft, but it's pretty firm, except where we're going to have dinner the first night, I think. November 2nd and 3rd. It's in the middle of the week. You don't have to worry about any basketball games or anything. Next slide. So on the 2nd, it's kind of a half-day meeting. It's more for PEIC board to meet and talk about what the next year is going to look like. There's a real nice social event. This has changed, though, so it'll be updated on the website soon. Next slide, please. And then this is a pretty juicy day here. So we're going to get tours of the NC State facilities. Power America is going to tell us their most recent achievements. And I don't know how many of you see the requests for proposals and the RFIs that come out of there, but they're really doing some neat things and really trying to help to get wide bandgap power electronics out into the market. They're not sitting and developing devices or materials as much as they're using off-the-shelf devices to build black boxes that do things and to just get them out there. Really important function. And then Tim McDonald from, I guess, was International Rectifier, but now part of Infineon, is going to talk about GaN standards because it's time, because GaN's really coming into its own. You got New York PEMC giving an update. Got Jem Bascari from Quora Technology to tell us about this innovative substrate technology. And then we've got a real user out there, John Deere, that's going to tell us not so much about tractors, but about other things John Deere makes and why power electronics are important for it. And then Power America announced the hiring of a CTO. I think it was earlier this year. Victor Veliadis has a really great resume. Came most recently out of Northrop Grumman in the Baltimore area with a ton of experience in RF, but also power electronics. So it's really a great team at Power America. And the PEIC is really happy that they're hosting this meeting because it's kind of, we're members in each other's organizations, and this was really helping us cross-pollinate. And then Dean Henderson had the idea of this trolley pub crawl. I don't know if anybody's ever done that. So you get in the bus and you can actually pedal. Everybody can. And you go from pub to pub and rub elbows with NC State students, I think maybe professors. Sounds like fun, and the weather is likely to be pretty good in the early November at NC State. Okay, summary and conclusions, last one. So I kind of put a statement together about each major section. That energy efficient lighting and power are driving wide bandgap semiconductor materials and devices, and as well as many other applications. Hopefully you see that Kyma's sort of a leading developer. I mean, I think we're the only ones doing that array of ultra-wide bandgap materials and GaN in the U.S. Maybe worldwide to have that full mixture. PEIC's a pretty neat organization. We need new blood. So if you want to come in and be considered for the next president, I'm looking for my replacement. But I'm loving the job while I have it too. So don't get me wrong there. And hopefully we're all seeing that wide bandgap semiconductor materials and devices are changing the world. It's going to continue, because I'll just ad-lib a little bit here that, gallium arsenide I think was developed for military radar. And then it became everybody's laser scanner, pointer, taillights, everything. Once you develop a crystal for one reason, then you leverage that to do all kinds of things. And there's plenty to do with the wide band gaps. So thank you for listening. I'd be happy to take any questions. Yeah.
You said that you cut the 7 millimeter diamond, right?
Yes.
So how will you make sure that the surface recombination is less? Because when you cut, there is high surface recombination, so you need to passivate the surface.
Right, for sure. So, yeah, boy, I'm even less expert in diamond than some of the other things, but there's a couple different ways to cut it. An ion implantation assisted laser heating, you can remove thin layers, if I'm catching you right. And you can actually lay those all aside and then treat the surface, with plasmas and special recipes. But we've been able to make really high mobility, relatively high hole concentration layers actually our Michigan State partners have demonstrated that. And so yeah, you never just slice and expect a surface to be good. There's subsurface damage minimally. And polishing diamond is a real challenge, because you don't have some harder material that you can put in there, because we use diamond slurries to polish gallium nitride, and then that's really nice. So I guess I'm not so much answering the question as recognizing you're right. You have to be very careful there. Yeah.
I just had a question about kind of the market in general. You alluded a couple of times. One, there were some idle machines that had been kind of written off already that they repurposed for a new process, and then how your company's elected to go with a tool builder, and that's their primary business. Mm-hmm. How do you kind of see that market evolving? And I guess from where it was all silicon and now there's these new materials, I mean, it seems like there's just a whole scatterplot of different types, and all of these are going to have different tools or different methodologies. And so do you see kind of consolidation happening, or do you continue to see things kind of fragmenting and moving out in other directions? Oh,
yeah, I definitely see consolidation happening. I think if we're successful in getting about 10 of these tools in the market, and it looks like they're being accepted, we'll be acquired in a millisecond. And I know that Applied Materials has hired and fired groups multiple times now in these very same spaces. And then they made one stick in PVD aluminum nitride, because they're not big enough to capture their attention until they are. And then when they got their attention, then they get out the big guns. So yeah, I see consolidation coming, sure. Yes?
Working in a material, we mostly consider nature dependence of the material to make it widespread. What do you think gallium nitride will extend with gallium nitride? How much it is naturally abundant?
Yeah, I don't know those numbers well. It's pretty abundant.
There's plenty of nitrogen.
Nitrogen's no problem. But gallium is a byproduct of aluminum mining, and And the gallium prices never got awful. Indium's the biggest question mark. So it's more expensive, it's rarer, and it's not used for power electronics yet. Could be. But for solid state lighting, the price and availability of indium's a bit of a concern, but I've not heard of concerns about anything else that I showed.
Yes.
Yes,
Definitely.
yes. At the same purity.
Like twice as much for the metal organic precursor.
And it's used way less because it's usually just in a thin layer of a structure. So yeah. But solid state lighting, I mean, once you get all of their long lasting lights, once they're all penetrating the market, then there's no more market, right? Sort of teasing, there's always new applications, but that one won't go on forever, for sure. And OLEDs are coming into their own at some point in time too. Yeah. There's plenty of carbon also, so diamond's good.
We are going to go up to the EPIC conference room. So if any of you would like to join us for a general discussion for the next half hour, 45 minutes in the